Hi, thank you for joining us for the AWS Education Research Seminar Series. I'm Marcy Collinson, your session correspondent and the Scientific Research Programs Manager for the Worldwide Public Sector at AWS. Today's presentations, which we have a dual presentation today, center around advancing the frontiers of science using extreme scale computing. It is with great pleasure that I introduce our first speaker, Dr. Dan Stanzione. He is the Executive Director of the Texas Advanced Computing Center, or TAC, and Associate Vice President for Research at the University of Texas at Austin. He is a nationally recognized leader in the field of HPC and is also the Principal Investigator, or PI, for a National Science Foundation Next Generation Supercomputer FRONTERA, the fastest supercomputer in the US at any US university. Dr. Stanzione is also responsible for TAC's Stampede 2 and Wrangler systems, supercomputers for HPC and for the data-intensive applications. For 6 years, he was co-PI at Cyverse and a large-scale NSF Life Sciences cyber infrastructure. Dr. Stanzione also is the co-lead at TAC's Ranger and Lone Star supercomputers deployed at UT Austin. He received his bachelor's degree in electrical engineering and his master's degree and doctorate in computer engineering for Clemson University. Dr. Stanzione will be discussing leadership computing in the age of cloud. I wanted to let the audience know that we will have a Q&A portion for this session at the last 15 minutes. For those of you on the virtual channel, feel free to go ahead and type your questions into the queue, and we will have a microphone for live audience members. And with that, I'll hand it off to Dr. Dan Stanzione.
Thanks very much, Marcy. I've got my own. I come with a microphone. Thanks. And yes, thanks for the patience for those of you, especially online. We're running a little late due to exciting fire drills. So I don't know if I'm nationally recognized, but you found me on the sidewalks outside. So at least I'm recognized on the sidewalks of Seattle. So I appreciate that. But thanks very much for the invitation to be here and the opportunity to talk to you. So what I kind of want to talk about today, in a nutshell, is tell you a little bit about us at TAC and what we do, and then talk about our latest project, FRONTERA, and why you might care. Turns out Amazon is actually a part of this project. And then I want to talk about several different kinds of workloads, right? Because we are still building our own infrastructure, and I'm here talking at the commercial cloud provider. And so I want to talk about why we still need some infrastructure for some of the stuff that we run and what sort of stuff that is. And I want to talk about what kind of stuff we have in the scientific workload that is much better off running in a place like AWS. And then I want to talk about some of the future science workflows and where they will run, and the answer is probably both for reasons I want to get to. So let me just start with a little background about the center. TAC's been around for a while now, almost 20 years, but before that there were various other HPC efforts in the university. The cluster on top in this image, Grindle, is the very first cluster I worked on. Back in 1993. It was the second of what became Beowulf clusters, which was sort of the start of commodity cluster computing. At that point, we had such industrial scale things as I was in my boss's garage laminating shelves for those servers that went on the machine there. And our goal was to get to a gigaflop for $50,000. And we've come a long way to FRONTERA now at 40 petaflops. It is also not $50,000. It's a little bit more than that. But at TAC, what we exist to do, we're at UT Austin, and we're a research unit that's part of the university, but we're primarily funded by the National Science Foundation. So we have, of course, a Texas mandate, but also a national mandate, and we handle a few tens of thousands of users from a few hundred institutions around the country to do open science research. We stay out of the classified business, but that's what we're there to do. So to explain us in one slide today, we have about 185 people. We have about 12 megawatts of data centers, which is the real measure of computational capability today. And our own chilling plant, of course, if there's any infrastructure folks around. We have lots of infrastructure stuff to talk about. But we also provide a wide variety of services based on, at the core, about 7 billion compute hours a year. We store about 5 billion files and a few hundred petabytes. And then in a wide variety of services, as I mentioned, we support at any given time 4,000 to 5,000 different science projects for mostly university users, a few industry ones as well. We have about 15,000 people who have the skills to SSH in and actually do something at the command line, who are sort of Linux experts and can work on those things. And then we probably have another sort of 3x that that come in and use the system through web portals and web services and sort of other ways. And we run with a demand at about 8 times what we can actually provide. So if we had 8 times the infrastructure, we would keep it filled. And this sort of is my slice on the workflow. You probably have a similar one in what you do in sort of scientific computing here. But fundamentally, I sort of group our workflows into 3 categories. And I think increasingly we're seeing blending of these categories. But traditionally, there's simulation. And simulation is basically anything in the physical universe where we can build a complete mathematical model, usually differential equation based, right? But we can build a model. We know the math of how a system works. And when we want to ask questions of that model to, say, design a new material or design a new aircraft or whatever it happens to be, we use simulation to do that. So numerically intensive, all based on sort of some fundamental math about how things work. If we don't have complete models, if we have either a partial model or we want to infer a model from data, right, that's where our machine learning and AI part falls into science, right, where we have maybe, genomics is a great example. There are no differential equations that govern how genomic information maps to phenotype, right, express behavior. So we need to build a statistical model. But in essence, what we're doing is asking questions of data, right? And that's what machine learning is all about for us, is we either have a model that we can ask a question of or data that we can ask a question of. And finally, and this is fairly new in the HPC space, is the scale of experiments have gotten to the point where we need to ask questions of our instruments when we run an experiment, right? And at the large scale, these are things like the Large Hadron Collider or LIGO, or in the not too far off future, the Square Kilometer Array, where the data rates are in the exabytes per month and into zettabytes per year of data, right? These are not desktop scale analysis problems like hooking an imaging microscope to your laptop. Or even a genome sequencer. And the other thing that I think Amazon's really in the forefront of is in the sort of Internet of Things side of things, where we can produce very small sensors that produce fairly small data streams, but then we produce ridiculous numbers of them, thousands of water quality monitors that are wirelessly connected, or tens of thousands of UAVs, monitoring wildfires, et cetera, et cetera. So we do sort of those 3 categories of work in science, makes up basically 100% of our workload. We stay out of administrative and all that kind of stuff, but we're asking questions of models, data, or experiments. And we've spent the last 20 years figuring out what the right systems look like to do that. So TAC grew up in almost the same timeline as Amazon growing up in some of this. So we officially became TAC in 2001, and we were a tiny little startup, scrappy startup, 12 staff, a $600,000 budget, 50 gigaflops of computing. And we've grown by a factor of several hundred thousand since then, not necessarily in budget and personnel, but still by a few factors of tens. And we've made it from these sort of, in garage-based clusters to steadily more larger and more professional-looking infrastructure. And as you also find, so 2007 was kind of an inflection point for us, not just because that was the first TAC award I was on. That's just coincidence. But Ranger in 2007 was when we did the largest open science system in the world. It was number 4 on the top 500 list at the time, behind 3 classified systems. And once you have sort of that level of computing resources and you've built all this infrastructure, as I'm sure you've discovered, you start to get involved in all the other things that you can do with it. So our portfolio sort of evolved from being the folks with the cluster, who would provide scientific cycles to people, to being the folks who are doing more and more of the workflow and the software and the services and getting involved in other things. So after 2007, everything up to 2007 is about building systems and getting funding to operate them. And after that was when iPlant started in 2009. When we sort of got TAC Life Sciences going, but it was a huge award to do bioinformatics, because now we were not only the people with the infrastructure, but some of the know-how on how to use it. And so you see, we've had not only bigger and more professional sort of systems as we've grown in scale, but also the variety of things that we do has grown. And so the workload in HPC has changed a lot in that time frame, right? So again, if you go back to the 2005 era, before we started getting into these other services, it was you stand up a cluster, you give people a login, and away they go, right? And you help them when things die. But basically, we're just handing out usernames and passwords to some extent. And people would show up, they'd bring a little data, they'd run their simulation, they'd take it home, and do sort of non-HPC things. But as the data volume has grown, there are no non-HPC things in most of these workflows. So we spend a ton of time on interface and on web services and on portals. I have on our staff now, I have about 20 people who manage the systems and the infrastructure. I have 40 that do the web portals and middleware, so that's actually twice as big as HPC in-house, and then another 50 or 60 doing various types of application build-out and support. We actually have 6 times as many software-oriented people as hardware-oriented people at this point, but 40 are just sort of in that front-end, middleware, web services sort of thing. So as we move from batch to interactive computing and event-based and streaming, and this is where our ability to work together gets bigger and bigger. So we've gone from just being the let's build a cluster to building sort of an ecosystem around scientific cyber infrastructure, which requires, at least in our view, a whole bunch of classes of computing and storage systems, and also a whole bunch of human services, and everything from dealing with reproducibility to data curation, and data schemas to the actual nuts and bolts of how do you scale a computation to 500,000 tasks. So with that as a little bit of background on TAC, let me tell you a little bit about FRONTERA, the project itself. So this is our latest and largest, actually, NSF system, and there's actually sort of 3 components to the project. One that we'll obviously spend most of the time talking about is building a giant system to do really the largest scale science challenges. So we actually operate about 15 different platforms right now. We still operate Stampede 2, which is in the top 20 in the world, and hardware-wise, they're somewhat similar, but the difference is in how we apply them, right? So Stampede 2 is sort of the broad mission. We have 2,000 different science projects on that, so on average, you're getting about a 2,000th of the time on the machine a year. FRONTERA, we want people who can use the whole thing for days at a time. So we're only supporting about 35 projects on that versus 2,000 because we're dealing with sort of the massive scale thing. So this is where we really see the differentiator between what I'd call sort of the pure HPC and these more sort of hybrid workflows. So step 1, build this awesome system. Step 2, we're going to run it through 2024. And we have a whole bunch of interesting operational things. And step 3 that we'll talk about in the end is we need to plan the sort of next generation of facilities for the latter half of the 2020s. And this is where I'd really like some feedback on how we'd work together on that. We're building requirements for that now. But FRONTERA today, on the top 500 list, it's the number 5 system in the world. It's the fastest university-based system in the world. The 4 systems that are ahead of us, 2 are in the US, 2 are in China. They're all heavily accelerator dependent. So if you have a general purpose code, we are without doubt the single fastest machine anywhere on the planet to do certain classes of computation. So it's the biggest one Dell's ever deployed. It's the highest ranked Intel system. If you look at FRONTERA and Stampede at number 5 and number 19, they're number 1 and 2 among US universities. And if you add up across the top 500 list for scientific computing, 77% of all the performance available to US universities comes from our data center attack at this point. So, but as you have also discovered, you start with a pile of servers, and then there's a lot more work to do after that. So FRONTERA is a great machine, but it's also more than a machine. Really, we think of it, again, as sort of an ecosystem of computation, right? So we have the main compute partition down there on the bottom right of the slide here, where we have about 40 petaflops in 8,000 Cascade Lake Xeon nodes. We'll geek out on hardware for just a couple minutes in next few slides. But we also have various GPU options. We have about 1,000 GPUs in the machine. Some are sort of desktop class GPUs that are liquid cooled. Some are the more enterprise class GPUs. We have a variety of storage options I'll talk about, all put together with a very low latency, very high speed interconnect, which is probably the primary differentiator. And then connections to the commercial clouds as well. So including Amazon's, you are a partner, and I'll talk more about that in a little while. And then we have a much thicker layer of nodes in front of the machine to run persistent services, where you used to have 2 or 3 login nodes and something to run the batch queue and other services. Now we have a few tens of nodes that manage various kinds of services that live in front of the machine, even with a small number of projects. So to just geek out on the hardware side, if we have any infrastructure folks out there listening who want to know a little bit about how to run this thing, we have in the main compute partition, we've pushed into the 200 watt plus SKUs, and a consequence of that is we've switched from air cooling to liquid cooling directly to the chips at this point. So, and this is the first time, well, not exactly the first time, but at large scale, it's the first time we've done liquid cooling directly to the processors. And we like it for a number of reasons. From an infrastructure perspective, it's a little bit harder to deal with. You get a You put a rack in the data center, you can't immediately fire it up because you have to tie it into the water infrastructure and have enough load, et cetera. But we have as you can see, there's 2 hoses that come out of the back of each node. So that's sort of a half-U node with 56 cores, about 5 gigaflops peak performance. But we have the cold water supply and the hot water return. It's actually not water at the node level. It's a glycol solution. It looks a lot like antifreeze. It's as sticky as antifreeze when you spill it, by the way. Not that we would have any experience with that, having installed 16,000 of those things. But so it glows green under the floor if it spills there. Again, just purely hypothetically. But the advantages of this is we can pretty much keep the processors at constant temperature. And if you're familiar with modern processor architecture where every millisecond you're adjusting speed based on thermal and power consumption at the socket level, we can run them. We had a pretty sophisticated air-cooled infrastructure around Stampede with just 150-watt sockets. But when you run every floating point unit, all 512-bit vector instructions, LinPack is the classic example, running the benchmark, but there are other examples of it too. We'd run the chip up to about 80 degrees C. So 180, 190 Fahrenheit. In this case, we keep the chips at 50 degrees C, even under max load, which means we're never thermal limited, so they actually run faster. So they run until they hit 205 watts, and they have to start slowing down a bit as you load up the cores, but it's done interesting things for sort of consistency of performance, and consistency of performance across mini servers is incredibly important to what we do. So that means we also build a lot of infrastructure. Again, we're nowhere near at your scale, but we do have sort of Dr. Seuss's worst nightmare of pipes out back of the data center where we build the chilling plant, and we've reached 60,000 watts per cabinet in the Frontera design at this point. So we have 5.5 megawatts of compute, which is small by your standards, but it's actually just 3 rows of the data center that get to that compute, and they're room neutral to do it. We are doing a lot of things. So with 205-watt chips, I like to joke that in supercomputing, we are both the cause of and solution to global climate change because we'll run the simulations to figure out how to do something about it and what's happening. But we're also consuming an awful lot of power to get there. So we do a lot of things green in the infrastructure around it. So we actually are more efficient by moving to direct water cooling of the chips versus doing air cooling on it. In the GPU nodes, as I'll show you in a moment, we're doing oil immersion cooling, where we directly immerse the entire server and run it effectively underwater. It's not water, it's not a conductor. But we run them fully submersed, which is sort of the maximum efficiency we can get in cooling. And we have a few hundred kilowatts of solar outside helping to run the data center, and we're buying about 1/3 of the data center power from wind at this point to run all this infrastructure behind it. And I should say, although we're using the highest power possible processor, which gives you, in theoretical flops, the theoretical flops per watt is terrible. But if you run, again, if you're into processors, or just silicon technology in general, there's sort of a factor of 3 relationship between frequency and power. So every 10% more frequency, you're using 30% more power, which leads to a lot of designs of a whole lot of cores at a lower frequency rate is the sort of low power design du jour, which gives you the best theoretical flops per watt. But people's codes can't use that as efficiently as they can the higher clock rates. So we find that our delivered flops per watt actually gets much better with the high-powered chips. So it's theoretically not as efficient, but in practice it actually is more efficient in terms of the total watts we need to do science on some of these things. Again, something else we have in common is nothing works if you don't get the cabling right. So we have a pretty sophisticated interconnect around this. Fortunately for Stampede 2, for Frontera, it's pretty compact. So we did it with just 45 miles of fiber because it fits into 3 rows in the data center. So it's a very compact machine. But this is a huge issue for us because latency is determined largely, increasingly a big factor in latency is actually the speed of light in the fiber. So the bigger we have to make the physical machine, right? We could do 30 kilowatt racks and have twice as many of them and have twice the footprint. We'd get a 20% increase in latency because of the actual speed of light and fiber doing that. So we have a very dense cable plan as well. We also do almost a complete fat tree. There's a tiny little bit of oversubscription, but it means we're bringing a whole lot of fibers at 200 gig. We're actually pulling 40 fibers out of each cabinet, and there's 90-something cabinets at 200 gig. So we have thousands and thousands of fibers that run together. And we're fanatics. I mainly put this up so we'd have the picture of the cable management. We're fanatics about getting to the core switches. So that's an InfiniBand HDR switch. Each fiber is 200 gig and with a non-blocking backplane to all of it. File systems is one place where we're very different. And just our experience with our users is getting them off of POSIX is virtually impossible. So it's Lustre and it's POSIX, right, is what we do. We have about 50 petabytes of disk and 3 petabytes of flash in Frontera. I have personally come to believe that most of our user codes are written just to torture us when it comes to the file system. You may have similar experiences. I think they look like this in source code. So while one fork open, and then I'm not sure anything else happens because they just seem to generate massive numbers of metadata operations. And almost nothing else, right? You know, parallel file systems are designed, so if you do 10 megabyte stripes to a 5 terabyte file on 100,000 cores, everything works great. And so the average file size is like 800 bytes, right? So, and the system optimized to do super large stripes. So, they might close the files. I find that users find that as optional, and then they run like 100,000 copies of that, right? So, and like I said, there may be reads and writes, but they seem to be dwarfed by the metadata operations. So, given that we think our users are sort of pathological when it comes to I/O, this is being recorded forever, isn't it? I just called my users pathological. It's going to go great. So, but nonetheless, what we've done is build these sort of massive Lustre things. We used to build one massive file system to support the whole system because to get the bandwidth we needed for the very highest demand applications, the only way to do that was to aggregate thousands of spindles together, right? So you build one file system with 4,000 or 5,000 disk drives, and we could get the sustained bandwidth that we wanted on the assumption that a single read or write would be striped across the entire file system. The age of solid-state storage means we don't have to do that anymore, right? We can scale capacity and bandwidth sort of independently. So we used to have one namespace for the entire machine. Now we actually have several. There's 3 different scratch file systems and then a separate flash namespace. But we can get more than a terabyte a second, about 1.2 terabytes a second doing writing, to the flash file system. So we can put the most I/O intensive applications there, and when users run while one fork open, at most they can trash one of the 6 or 7 file systems and not the whole machine. That is the most fragile part. Again, we'll come back on that in a moment. So then the question becomes, given that we have all this infrastructure, why are we also in the business of doing commercial cloud partnerships with you guys? And I have long maintained, and Sanjay and I will probably argue about this before the day's over, that cloud and HPC is not, in my opinion, an either-or question, right? We have sort of different strengths, we're different tools, right? And for the most part, in computing, like in anything else, if you show up to do a job and you bring a toolbox because you're going to put a roof on a house, you probably have brought more than one tool. And that's okay, right? Not everything has to be one size of hammer. And so what we want to do is utilize the strengths of commercial cloud where we need it in science. And so initially we want to partner with you guys in 3 areas where you can do things a lot better than we can. One of them is long-term data publication, right? It's not unusual for somebody to come in and run on the machine and maybe build 100 terabytes of historical hurricane data, right? Thousands of ensemble tracks from big simulations. But then you want to share those out with people over years, and people want to come in and do queries and do analysis on those tracks, right? And the cloud is a perfect place to do that. You also have a little bit larger infrastructure budget, I hear, than I do. It's disappointing, but I think it's true. And we deploy a big machine every couple of years. You guys deploy a bunch of hardware every month, so you have a lot of unique hardware that we can't see. You have a lot of the latest of everything coming up sort of monthly, and getting access to that to understand how we want to evolve our infrastructure is pretty important. So access to this unique and ever-changing hardware. And then finally, and what I think will be the most important over time, is this notion of hybrid workflows that we stitch together via web services. So I'll talk some examples of that later in the talk. This will come up. But this notion of use the cloud where the cloud is the best tool and use HPC where it's the best tool in a single workflow, I think will be important. So with that, I'll stop talking about systems and stuff and say, let's talk about workloads, right? So first off, and I have sort of 3 classes of workloads I want to talk about. And so first of all, what kind of things do I think really need to run on a system like Frontera? And then we'll get into the why. So I have 5 sort of recent examples. So we took the machine aside for 2 weeks and let sort of one user at a time run the whole thing. So the entire data center and infrastructure on single problems. And we found that we had at least a half a dozen that can actually get to sort of that scale. So And these are sort of the types of problems. So this is Alexei Aksamentev. He's at Illinois Urbana-Champaign. Physics of living cells. So he sort of worries about the pores at the nucleus of the cell and what gets in and out, which has drug delivery, disease mechanism sort of applications, and a whole bunch of other ones, right? If you want to get stuff into where it really affects how your cell metabolizes things, this is where you do it. So, and really to understand these pores around the nucleus, you had to sort of go down to the atomic scale. So he's using a molecular dynamics code called NAMD. And with a machine like Frontera, we can run really, really big systems for him. So, used to do this with sort of 30 atoms and try and extrapolate to full material. He's now at 150 million atoms that we're doing, simulation of the actual sort of movement of molecules at the 150 million atom side. And even with this, so he ran on almost the entire system. So 7,780 nodes, 56 cores per nodes. He was using on the order of 425,000 cores, tightly coupled threads, and then updating at sort of femtosecond resolutions of the time steps in the simulation. So every femtosecond of simulation, you have to exchange state with all 425,000 other cores. Use a code called NAMD, which is a nice code at small scale, but getting to this scale is kind of hard. He got linear scaling out to several 100,000 tasks and was able to keep scaling at not quite linearly, again, all the way out to the size where you can get several petabytes of RAM, which it takes to run the system at full scale. It's probably, if not the largest, certainly one of a handful of the largest biomolecular simulations that's ever been run. And based on this, they're going to try 300 million atoms, which they didn't think they could do, and get, eventually we'll be able to do a full cell at sort of this scale. A similar one also in sort of molecular mechanisms around biology. This is looking at HIV studies. This is Greg Voth at the University of Chicago. They use a couple of different codes, LAMPS and NAMD. I think this was also a NAMD run, but they were trying to do full atomic detail of this HIV capsid for 500 nanoseconds, right? And understand every atom in it so we can really truly understand at the molecular level what drives this, right? For basic physics. And they scaled to 4,000 nodes and have nice quotes about why they need really large-scale supercomputing resources. So Carlton is at Utah. It's a very different problem. He's doing quantum chromodynamics, so this is sort of basic theory of matter type stuff. And well, you can do a lot of things based on quantum chromodynamics, better solar cells. There's all sorts of applications, but essentially it's building engineering materials up from first principles, right? Do we really understand, how matter fits together, right? So if we need to replace silicon, some of the work will come from quantum chromodynamics in the future. So he's also gotten to the scale of several 100,000 threads, but this, for them, they were stepping up to, not used to being able to run at sort of the scale. They ran 16 times larger problem than they had ever run in the past of their lab. And now they're like, well, hey, we actually can get to exascale at this point, is sort of the theory here. And then another user at Illinois, but very different domain, Dan Bedoni. Dan's work is in hypersonics. Well, he's mainly a turbulence guy, looking at turbulent flows, which apply in everything from high temperature combustion to plasma streams. But in this case, we're looking at hypersonic aircraft. So if you believe that the flights from Austin to Seattle are too long, this is your solution. Fly at Mach 12. So I think anything over Mach 2 is considered hyper. It's like Intel and hyper-threading. So these are hypersonic vehicles that they're looking at. And you need to do very fine eddy, refinement of the eddies to understand how this works. Turns out, turbulence affects drag. There's so many things. So actually, golf balls have dimples because of turbulence, right? So you try and create a turbulent flow around the golf ball so it flies further, and we need to do the same thing to create stable aircraft in essence. But they actually got super linear scaling out to several thousand nodes because they were actually fitting more of their system into the sort of on-chip memory. And eventually were able to fit their whole system into cache, which was huge for them. But again, really tiny time steps to move this forward and understand the eddy resolution. So, and then Paul at Minnesota is doing 3D stellar hydrodynamics. So in this case, he's looking at boundary mixing in really large stars and the different sort of layers inside the star. There's also fusion power applications to this, but fundamentally, this is sort of basic science and astronomy. This particular run is probably one of the largest single computations that humanity has ever done, because most of these things, because the network is inadequate and various other reasons, get relatively poor percentages of peak out of the machine. And this one, he was actually able to sustain about 600 gigaflops per node, which means we had sustained performance of multiple petaflops on the simulation. And we were able to run it in one chunk for more than 80 hours on 7,300 nodes. So again, about 400,000 CPU cores applied nonstop for 80 hours. And there's no restarts or failures or anything in there, right? It has to be completely clean and at the same speed across that. So, so these are sort of some of our largest runs, and I think HPC. So what do we have that could run on the cloud? And then how do we tell the difference is really the hard thing, because you might think they look similar. So, so these are some workflows where we pulled in and looked at where people are starting to move to containers, right? So we have really slow evolution of software, but we see some. So these next three examples are all completely containerized workflows, but still sort of big science things. So Mike Gurnis is at Caltech, and he's, I think, a Gordon Bell Prize winner. He's been on the cover of Nature for this, and they study sort of the fundamental mechanisms that drive how the continents move, which means understanding how things are, what's going on inside the mantle of the Earth, right? And what are the fundamental dynamics of how that moves. And it turns out it's liquid rock, which is a non-Newtonian fluid at very high pressure and very high temperature. This was on the Stampede machine, but they use a code called Underworld. They think they're clever, but subsurface stuff. But it's a mess of packages, as you might imagine. So we've built this whole thing into Singularity at this point. And he can do sort of scales, different size runs using Singularity and fairly portable between machines. Dave and Tom, Tom's at Austin, Dave is at UCSD, do PDE work. Tom sort of invented the finite element method, or at least wrote the seminal book on it. He has, if you look him up and search his H-index, he has like 15 times the number of citations of Isaac Newton. So he's done okay as a scientist. So, but they use a code called Phoenix, which is this finite element method package that's Python and Fortran and C and a whole bunch of stuff, and a giant mess. And again, they have built this into a container system, and they can move between infrastructures at different scales. And they're doing this sort of coronary artery flow work, using the finite element method. But it's a completely containerized workflow. And then Sharon, who's at the University of Michigan, does this colloidal crystallization work. I'm not super familiar with this, but it's a sort of, again, a molecular simulation, sort of shifting phases of matter between solids and fluids, and sort of understanding how this happens, and sort of gel suspension and stuff like that. Also a completely containerized workflow. They can run on 5 or 6 different supercomputers at the same time, which is an important indicator that maybe this is a cloud-suitable kind of workflow. So, so those were all sort of bright red and black science-y looking slides, right? So what is the difference between these two things, right? So because we're webcasting, I can't stop and ask for questions. But let's just say you asked, hey, all those things sounded like really science-y kind of things with big workflows. What makes some of them sort of cloud-friendly and some of them not? And so I want to spend a few minutes on just sort of discussing what makes a workflow either friendly or unfriendly when we talk about moving it to sort of different classes of machines. And so first of all, it's not necessarily scale, but as I'm sure you have discovered in growing up, you always find new problems at scale. So scale exacerbates these problems, but scale isn't sort of the root problem between them. I think there's sort of 3 classes of barriers, and there's, and I gave up trying to classify them into these, so you can decide which one's which, but there are social things, which if you could get the people to change, we could change the technology that underlies it, and we could make these things run in sort of a cloud-native way. I try and stay out of things that involve changing people, because we're remarkably unsuccessful with that. Technical stuff's easy. We have some technical things that sort of don't work now, but with some infrastructure tweaks, these could be fixed and stuff could work. And then we have some structural problems that I think aren't going anywhere in the near future, even if we try. But many of these things, and I just sort of built a laundry list of them, could fit into more than one category. So I'll let you decide which one's which. You gotta have some fun here. So I think the number one thing that we always talk about that really separates the sort of first 5 applications from the next 3 applications is latency on what we call large-scale collectives becomes the dominant factor in performance. I happen to know, because maybe we've gone in, that you have your elastic fabric interface, the EFA, and that if we tune an MPI library on that, we can get latency down to 15 microseconds, which is awesome, because if you look at like cheap commodity Ethernet, you get like 100 microseconds. If you look at like good switches and high-end cards and good commodity Ethernet, we get like 50 microseconds. Your latest network infrastructure is at 15, which is a huge step forward. But our worst case latency is less than 2 at this point, microseconds. And our in-rack latency is below a microsecond. You know, if you're sticking within about 1,000 cores, we can do it 900 nanoseconds. And then in node, we're at around 200, maybe as high as 240 nanoseconds. But we're in the several hundred nanoseconds, right? And so this is where we get into speed of light and fibers, right? You know, it takes a nanosecond for light to go this far. In Texas speak, that's 30 nanoseconds for a first down. So we have 100 meters fiber, worst case, in our machine, right? So we have 300 nanoseconds coming from, of our less than 2 microseconds latency is coming from fiber, right? You know, just the speed, you know, and we seem to not be able to speed these photons up. I've asked for upgrades. It's not happening so far. So we need this sort of power-dense rack layout. We need a max radius on the machine, right? You know, if you remember the very old Cray supercomputers, they were round because they were trying to run, you know, across every wire in the machine inside of a clock cycle. We're a little more asynchronous than that now, and we can tolerate a little more latency, but still, there are codes, and those first ones are mostly in that category where you almost scale linearly with network latency in terms of the performance, right? So if your latency is substantially worse, you're going to expand the runtime by 6 or 7x per job, even just to go from 2 microseconds to 15 microseconds. So that's sort of a huge technical barrier. And again, not every code's that way. And again, the ones that are containerized and scaled down, and you can do a lot of ensembles and stuff, don't have that behavior. So, but there are still some that's the sort of key behavior. The other one is sort of failures, mean time between failures. Here I don't just mean hardware failures, also soft failures, right? So if we look at a scale, so Paul's code, 7,300 nodes, we ran it for 80 hours, right? You couldn't reboot anything in that, right? No hard or soft errors. And we were running, you know, if you have 8,000 nodes and you got to run them for days on end, that's the equivalent of getting more than 600,000 server hours without a reboot, right? And linear time, if it was one server, that means no reboots for 70 years, right? And that is hard to maintain that level of reliability. Now, most of them we don't drive quite that hard. We do enforce checkpointing, but I still need to do large runs, more than 200,000 hours mean time between hard or soft failures on the machines, right? So, and yet, so recently we did these sort of 10 days of large runs. We had to reboot one node at one point in those 10. But I really need that level of reliability, and we need it with this low latency, right? So I need repeatable performance. So you have to be extremely aggressive in how you tune out marginal hardware. You know, if you start seeing correctable DIM errors, that DIM's got to go, right? Because one, it's going to go slowly, and two, that's maybe a precursor of future errors to happen. And we have to be equally aggressive in tuning the OS. And sort of related to that, very closely related, where we do the same sort of things, is having reproducible performance and limits on these things. So, so we want to have less than 3% variance in node performance for all nodes over time, because varying performance is effectively the same as latency, right? When you have these tightly coupled things and we're updating every femtosecond what goes on in the simulation, if one's running a little slow, everybody else stops and waits for it. So now you have 400,000 cores running slow because one is. So we have to viciously reject components that vendors say are acceptable, right? We have, you know, for processors, we can tell which cores have been disabled, right? Since every SKU doesn't really use all the cores on the die. And, you know, we have gone back to major processor manufacturers and say, these patterns don't work because they're where they sit on the memory ring changes performance enough. And you shouldn't call these platinum or gold. And we've actually reclassified SKUs on processors to say these need to belong, you know, things that have this bit pattern belong in a different SKU. So we have to rigorously monitor temperature. And if you develop firmware, I'm out to find you and kill you. Short answer, because we've had more. Can't tell you how many power supply firmware issues I've had. And I'm like, look, just give me 2 resistors that split the voltage and give me the power I want. You know, analog still works. But yes, things that are there to protect the hardware from overheating, and processors will shut themselves down anyway, have caused no end of throttling scenarios. And we're like, can't you just turn this stuff off? But firmware is a nightmare for us at this point. We've done, you know, gone into firmware to do millivolt tweaks on phase lock loops and things like that. So to get the performance that we want. And I have to tell you, the vendors who we buy the stuff from have said a million times, we're like, hey, you have this problem. And they're like, oh yeah, but that's below the threshold where any cloud provider cares about it, so we don't fix those things. So that has become an issue for us in terms of sort of individual component reliability. And the other thing to get reproducible performance that we have to do is never share nodes, right? So on these large ones, one, because we can't enforce memory limits, and C groups and the other kernel mechanisms are not perfect. Enforcing memory limits, there's various race conditions to get around them. But workloads on other cores can affect your frequency, your power, and your thermals. And we can't live with that, right? Because then you'll get this variance in performance. You get variance in the available memory bandwidth if there's stuff running on other cores. And you get variance in the net injection bandwidth, how much network bandwidth we can get to get data in and out of the nodes on that. So, so we absolutely can't support node sharing to make these run. So at scale. So a few others, namespaces and file systems are the big ones. And so this is sort of the number one thing in dealing with bursts that we deal with. But we have an embedded base that has a lot of code that lights POSIX, right, in terms of the way it works, right? And so when I say file systems, I might mean, in some cases, petabytes of shared data that they expect to see, in sort of uniform access to everywhere across where they're running, where you can run an open and where you can run an LS. And persistent often means for years on the machines. I think my favorite saying on this is objects are for codes and files are for people in terms of the way they think about running them. So object stores are great for building system software, but our users want to see files and they want uniform access at roughly a terabyte a second to those files, right? So, and then finally the worst part, and this is the part where we also suck at this, so don't want to get this wrong. File systems are by far the weakest part of our systems and the thing that users can break the most. But you need to have at least 250,000 tasks that can simultaneously and coherently open and read and write a single file. And that's brutal. And 250,000 seems to be where most of it breaks at the moment. But so I won't say we're good at this, but there's really not an equivalent file system out there. So the behavior thing we need to change is users don't tell us what slice of that namespace they're going to use, right? There's a 50 petabyte shared file system. We have to assume they need to see it all, right? Because they just won't tell us what their slice is. That's a thing we could change behavior on, and we could encapsulate what part of the namespace they see. We could move stuff a lot easier. But the technical part is the intransigent old codes. And so how intransigent are these old codes? I'm glad you asked me that. So, so let's take, say, WRF, which is the current sort of state-of-the-art weather code. It's actually slowly being replaced by another one that grew out of it, but it replaced one called MM5, and they're all basically the same code, and they go back to 1975. AdCirc, storm surge, it's on sort of year 30 of development, roughly 1 million lines. All these codes, 35 or 40 years of development. Most of them started in Fortran. The core of them are often still mostly in Fortran at this point. 10 generations of postdocs and grad students and programmers have worked on these codes. The Department of Energy estimates their investment in each of the big community codes they use about $400 million a piece in terms of building that software, so way more than the hardware costs. So if we wanted to rewrite this and say all we want to do is switch to, maybe port a code out of CUDA to use just the OpenMP5 directives for accelerators. So there's some new machines coming in at DOE that are going to use the AMD accelerators, right? So it's a fairly simple rewrite when you get down to it, but it's in a complicated million-line code that people need to verify and trust, because they're doing ridiculous amounts of hard science with noise, LIGO. The signal-to-noise ratio is ridiculous. But so they, in the DOE exascale project, they're supporting about 30 applications. They're spending $30 million a piece to move the code. So that's a $900 million investment in software to run on the machines, right? So on Stampede 2, we've run 4,000 distinct codes over its lifespan so far. If you spent 30 million in each of those, I need 120 billion to update the code base. And so I've looked at my budget, and let's just say not going to happen. So on the 120 billion. But so these are very intransigent codes that are expensive. So we have cloud native apps that are popping up all over the place that deal with new models of I/O. But these old codes, again, my average staffer is younger than my average application. So these codes aren't going to move fast, and they're easy to break too. And I would say they stick because the cost of the resource is dwarfed by the porting costs, and this is huge for us. And in fact, it's not even really that they're old. There's new tech codes that have the same problem. It's the technology that the code started in that seems to have more to do with where it can run than anything else. So for instance, just to mention a competitor here, right, twice I've run into things where they started developing the code with Bigtable, and so it's stuck in Bigtable, and it's not going to come out because the fact that they're maybe spending a few tens or hundreds of thousands of dollars a year on the infrastructure to run that where Bigtable works is preferable to even attempting the rewrite on it, because that's a multi-million-dollar problem. So it's not just POSIX versus objects or Python versus C. It can be I started in Bigtable. And in fact, I think at this point, we have a whole class of machine learning codes that I would call GPU native, right? And even if we get HBM on processors in the same memory bandwidth and the performance advantage of GPUs goes away, which could happen, those codes are still going to run better on GPUs because they were built for them. And moving the code is harder than moving the hardware by a lot. So let's just stop there on that. So there's a few other things worth mentioning just quickly, and I promise to wrap up pretty soon. The team size is a huge part. So the bigger projects, the Large Hadron Collider, IceCube, these sorts of things, they have full-time people who worry about the infrastructure and the code. Your infrastructure is based on having full-time people who worry about infrastructure and the code. A lot of the teams don't, right? They have a couple of grad students. They've downloaded this code. They're making some modifications to it, or not. And it drives several things. One is the kind of scientific support we have to provide, right? So our TAC tickets are, well, I was building NAMD 4.5 with MVAPICH 2.4 and FFT 7.2 on MKL 19.4 using the Intel compiler. I get a linker error, please help. End of ticket. And then we just have to fix it from there, right? So you get a very different sort of role if people don't know between the difference, many of the software services. So, I have people who've built NAMD, the molecular dynamics codes, who've done research with NAMD and can get in and talk these people's language and work their way out. And startup importing is similar, right? So we've maintained in HPC a consistent user environment really for decades. We've added to it, but the basic parts of it look the same. So when I did early user for Stampede 2, I sent out an email to about 100 projects and say, we've turned your counts on, right? And within 14 days, I had 50 of them reporting in production science results. And we did maybe a half a ticket per project to support that. We had to answer a few tickets, but most of them could just start on their own. And then I could make pretty slides like the ones I showed, right? But I could get 50 of those within 14 days of starting early user. But in contrast, we picked 6 Science through Internet 2 as this project funded by NSF called ECAS, right? And they're using AWS, they're using Azure, they're using GCP. We picked projects who in their proposals all said they were ready. And by the way, when I say go, we don't give them any funding. They just figure it out, right? They get on the machine and they run. In this case, we're giving an FTE of funding to get them to move their applications. We're 5 months in, they have a few results. The kind of sort of almost working on some of these things, still tweaking things. The path names are too long and get truncated and blah, blah, blah. So some tools don't work, and but that's 6 projects, 5 months, really no early results versus 100 in the first 14 days, and that's because we've never changed the basic user metaphor. So the interface in the cloud is mostly really for developers, right? People who do know the difference between VLANs and VMs. And most of the first-year science grad students who've been forced to write Fortran don't know that. So the things that do make it friendly, containerization is always a good sign, right? If teams have containerized, 1, they've thought about portability, 2, they've thought about encapsulating their app, and 3, they've actually heard of containers, which I think is a good sign in terms of selecting scientists to do this, right? They've used some of the grid software like Open Science Grid, right? This means that they have a lot of computation versus the amount of data they have to move to use that environment successfully. So those are going to go straight to the cloud with almost no problem. And then we actually track all the linked libraries that people use and how they use it. So if you haven't linked an MPI library or you've linked an MPI library and you're doing things like just using it to launch 50,000 replicas and not doing massive all reduces or exchanges of everybody one to your left, then that probably means you have a cloud-friendly app. And the last barrier I'd mention is actually cost. And so it isn't central, but it is a factor. I've tried to do all those other things without talking about costs, but there's the absolute value of cost, and then there's predictability and variability of it on a grant budget, which means you get a chunk of money for 3 years, you're paying a student, you have a little infrastructure money. But in the next 3 years, your only way to change that amount of infrastructure money you have is to not pay the student or something like that, or worse, for a faculty member not paying themselves. And so, that's not going to happen. So, So there's, sort of the cost per node, but also the efficiency of using that node. And the thing I hear the most from users on, they gripe about, is egress costs. So give that as feedback. So given all that and all these differences, what can run on both at the same time, right? And this is where I'll finish up, because it turns out when I think about stuff that can run on both Frontera and the cloud at once, I also come to my slides on what does the future of science look like. So I think that's an encouraging sign for how we might be able to do some of these things. So here's a good recent example of things that was both cloud and HPC driven. So back in May, we got the first image of the corona around a black hole. Everybody calls it black hole imaging. You can't see a black hole, it's black. But you can see the corona around it as energy is ejected from compressed matter as it falls in. So they did this thing, and this was an enormous sort of global scale science project, right? There were 8 telescopes on 4 continents, I think, involved. There was a massive amount of data. Some moved via network. There were plane loads of disk drives coming from Antarctica, and things like that. But in the paper that came out on this, that actually announced this, and it got wide coverage, the New York Times, NSF director stood up and waved about it. So, but there were 4 different tech projects that got cited in this. And some of them were traditional HPC, as you have to do mass estimations to do the imaging to begin with. And so we'd done simulations back on Stampede 1 as far back as 5 years ago to make this happen. And we had to do a lot of new simulation runs to sort of figure out what you're looking at. But then the actual data analysis to get the telescope data into form to build around those simulations was a cloud workflow. And we have a sort of cloud testbed project with Indiana called JetStream, where that workflow got developed. But then the production data analysis actually ran in the commercial cloud with pipelines designed on some APIs that we built, which was the 4th simulation. So we did the simulation on HPC, we did the high throughput data analysis in the cloud, and we got these sort of groundbreaking results, and already rumors about things like Nobel Prize for them in the future. Which is a good measure of output for us. So we see these kinds of things. We see more tightly coupled ones as well. We're working on a project with DARPA in synthetic biology initially called Synergistic Discovery and Design. In this, we have data acquisition teams, some with flow cytometers and genome sequencers and mass spectrometers and like robotic phenotype systems where you have a bunch of robots that run 100,000 automated experiments, all event-driven workflows driven from simulation. But that data comes in from the experimental facilities. We process that into a big corpus of data. And then we have data analysis teams on the other side, about 15 different teams at companies and at universities who come in and run machine learning analysis on that. And of course, they're never going to download this data. We're bringing in many terabytes a week. It's a petabyte scale data set. But we need to link all these things together, right? The event-driven workflows to drive the instruments on the one side and to gather the data. The data quality is sort of large-scale processing and these sort of whole data runs. And then the individual ML runs by the analysis folks. So again, we have this sort of mix of a big corpus of data and things like that. And I can give 100 more examples of this, which I promise I didn't make slides for. We're doing acute and chronic pain things in the opioid crisis for NIH. That is definitely a hybrid workflow. We do an enormous amount of work in natural hazards, and so in one of our projects, Design Safe, just around hurricanes. We also deal with earthquakes and other things, but there's massive ensemble simulations of storms, an HPC problem, massive storm surge and tidal models, HPC problem, LiDAR data sets for ground and building elevations, sort of big data, Internet of Things type problem. There's rainfall models and again, Internet of Things type gauges in the field to do a massive freshwater flooding model to get the stream networks and rivers for downstream. There's a huge amount of image data ingest from UAV and space and aircraft and ground reconnaissance photos for everything from first responder to damage assessment. And then everything ends up in a GIS desktop system, remote desktop, perfect cloud application. So we can say, all right, here's the list of addresses that were flooded above the electrical outlet heights, which by law FEMA has to go inspect before they can let people back in. Or if you're directing your first responders, they're never going to get down this road because the bridge is going to be gone, so you need to send them another route, right? And sort of things like that that are real-time and analytics that can run in the cloud, but built on a bunch of simulations that need HPC in the front. So if we look at what these sort of future workflows are going to look like, and again, I have endless examples of this, but a lot of it experimental data to start with, a lot of analytics, a significant machine learning or surrogate modeling component on the other side, and then a big shared corpus of data that we need to collaborate and publish around. And so somewhere in this massive amount of simulation to extrapolate, test, and use these models built from these experiments, we're we're going to need more than one kind of computation to do this, and these are the things we want to build partnerships around. So second to last slide, so the next thing we're building is this thing called the Leadership Class Computing Facility, and right now we have the mandate to plan this, to say what does 10x the scientific capability of Frontera actually mean? And it may not just mean floating point, right? What are the scientific challenges we're going to face? What's the mix of computing and data and human resources we need to put in a facility to tackle them? And what do these cloud HPC workflows look like from 2024 to 2029? And I'll leave you with that to think about, and maybe we can talk about it in questions. But let me just say thanks to all the people who give us money and all of our partners and my great team that makes this happen that still fits on a slide. And with that, I will stop. So thank you very much.
Thanks, Dan. I'm going to go ahead and read aloud a couple of questions that came in through the queue. So if you wouldn't mind just staying up there for a second.
Absolutely.
How do we interoperate with Frontera and AWS?
So we're actually building that out now. So the formal start of operations was October 1st. So we're actually building that out, and figuring out namespace is the first thing. But the thing we're building out right now is there's a web portal in front of all this where you can manage all your data on the systems, and we want to do data publication push to the cloud. So in essence, we're going to keep it not from tying, you're not going to log into Frontera and directly do stuff on Amazon. You're going to log into the Frontera portal. So we have a web interface and be able to route your jobs to either Frontera or to Amazon, and to move your data from Frontera to Amazon and publish it and keep it there. So the interface is going to be at the web portal level primarily, I think. So.
Great, and we have a similar question, is just kind of how do we get started with using Frontera and AWS, so I'm assuming that's about the same answer.
Yeah, so you'll need to come to the Frontera portal. We do startup accounts for just about everybody, so either on Frontera or Stampede. Again, Frontera, we try and restrict to some bigger projects and then push everybody else towards Stampede. But you can come to the TAC portal and just request an account and then ask for startup access, and we'll go from there. So.
Perfect. I think that's all we have for right now, but we'll go ahead and keep them coming through the queue. We do have a virtual presence going on, so if anybody in the virtual audience has any questions, feel free to just keep entering them in the chat. I'm going to come up and introduce Sanjay. Thank you so much.
Switch laptops here. Thanks, Marcy.
Yeah. So, So we have a second presentation today for the dual presentation, and our second speaker is going to be Dr. Sanjay Pati, who is the head of AWS Research US Education at AWS. Dr. Sanjay Pati leads the AWS research initiatives, including AWS's federal initiatives with the National Science Foundation. He is a physicist and adjunct professor at Brown University. Dr. Pati has more than 15 years of experience in large-scale distributed computing, data analytics, and machine learning. He is the co-creator of the workloads management system currently used for all of the data processing and simulations by CMS, one of the largest experiments in the world at CERN, consisting of more than 180 institutions across 40 countries. Dr. Pati obtained his PhD from McGill University in high energy physics, is the co-author of more than 900 publications, and is also appointed by the Dean of Faculty as an adjunct professor of physics at Brown University. And he's going to be talking about transforming research and collaboration with scientific communities today. So I'm going to go ahead and hand the mic off to him.
Thanks, Marcy. So thank you so much for coming this morning. So I'll talk a little bit about how are we transforming research, what are the fields we're working in. Thanks for a very nice talk. Oh. So No. Just mirror it, right? Perfect. So thanks so much, Dan, for such a fantastic talk. One thing I completely agree that we really need to collaborate with each other. FRONTERA is an excellent machine, and this is one of the leadership class machine in the US. So what I'll talk about a little bit about how, what are the areas of research we're working on. So typically, as you know, that spans two kind of folks. One, people who perform research, and the folks who support research. So if you in general, it has many phases. For example, for research is global. It has security and other compliance areas. In research, analytics plays vital role. Also, researchers works in collaboration. So they require what we call collaborative tools and algorithms. So if I look at the last National Academy report, what you can see is essentially is that many fields today rely on what we call high throughput computing. If you look at the last two Nobel Prize, which Dan also showed, one went in Nobel Prize in Physics for Higgs discovery, and the second one went for LIGOs, for gravitational waves, and both of them uses distributed computing. As the previous speaker said, I came from Large Hadron Collider. So LHC is a collaboration of many countries, 40 countries. This is one of the silicon detector which detects a kind of particle. This is the CMS detector. It has roughly about 80 million electronic channel. So if you put 4 bytes per channel, and it operates at 25 nanoseconds, which means you're talking roughly about 10 petabytes of information per second. The question is, how do you analyze 10 petabytes of information per second? So what we try to do there at LHC is divide into 2 sections. Section 1 is do it at the site using something like FPGAs. So I'll come down to that. So this way you reduce the data rate and then do offline analysis. As depicted, this is one of the detectors. So each circle detects a kind of a particle. At the end, we combine them, and that's the size of a human. So in terms of data rate, it starts at nanosecond level, and then we reduce it at the trigger. We call it high-level trigger level, where people use FPGAs, and then an offline analysis is done at the second level. So FPGAs, I talked about FPGAs, just a brief introduction between CPUs, GPUs, and FPGAs. CPUs are roughly about 10 to 100 processing cores CPUs have. GPUs have roughly about 1,000 processing cores. But if you can program in FPGAs, they have 1 million processing cores. So once you classify into online sector, which is done by triggering, then batch system does the reprocessing. So in this particular example, I tried to show elasticity, an example of elasticity for a given static system. That's the total number of compute resources. For any reprocessing or simulation workflows, as you can imagine, these are peaks. So people tend to modulate elasticity, but with the delay in processing. So one of the way one can model it is really what we call bursting or elasticity. So in this particular example, we recently worked with Fermilab, later on the project called HepCloud, in which we changed the schedule itself such that it auto-burst once the Fermilab facility is full, using a simulation workflow to AWS, exactly the same environment. So there is no difference for the environment. The user doesn't even notice whether he's running in Fermilab or in Amazon. And the beautiful is not only running about 60,000 slots in a Spot instances, but also these ups and downs. So ups and downs tells you, and this ran for weeks. Ups and downs tells you that when the jobs are no longer in the scheduler, the instance self-terminates. And rising up shows that when there is new set of simulation job comes in, it basically picks it up. So this was recently demonstrated automatically, because at 60,000 scale, you cannot have humans doing the job. And now it is a DOE project called HEP Cloud. It provides that for many of the DOE users. So the architecture diagram was extremely simple. User submits its job to a central pool facility. When it's needed, it goes to AWS in a given region, instantiate it exactly in the same environment, shrinks it back. It supports, for example, CPUs as well as accelerated computing like GPUs. It supports checkpoints and migration. It supports remote system calls. It supports, for example, matchmaking. For example, I like to match to 6 GV or 10 GV node rather than 2 GV. So that does that matchmaking. It also supports DAGs. If you don't know or not DAGs, it means imagine I have 100 jobs, and once 100 jobs are done, then start 2 jobs. When 2 jobs are done, start another 50 jobs. That's called DAG. So you send a full DAG into the system, it automatically expands, does it, and follow the path. And DAG can be this format or can be diamond format. That means you have start with 100 and goes down. One of the major features is we recently changed the software such that it automatically interacts with Amazon S3. So Amazon S3 is our source storage system. So this way you do not have to go and upload your file to Amazon S3. All you need to do is in your job description, say this is my location of the file, and this is the location of S3, and do it. So itself, when job starts running, it auto-transfers to Amazon S3 all your input as well as output file. We recently implemented this for LSST workflow. LSST is one of the biggest telescope planned to be operating this or next year. We also work with NOVA collaboration. NOVA actually detects neutrino it originates at Fermilab. So how many people of you know neutrino? OK, so neutrinos are massless particles. It passes us all the time. OK? What's so special about neutrino? One of the special thing about neutrino is that it changes identity. It's very difficult to, so imagine you start with a Lisa and you detect a John. That's very rare. And that's what we try to do in this particular experiment, where a set of neutrino was sent from Fermilab under the ground and detected at 500 miles apart at Minnesota within milliseconds. And all you need to do is ask what is your identities are. Since you sent one at Chicago, you know you sent a muon type or an electron type. You're expected to detect exactly the same. In this particular study, it shows significant differences with respect to the one you sent and the one you received. So details is there in this particular article. So elasticity, you can model it many ways. So in this particular case, we model it using HD Condor as a batch system. We were trying to recently study natural language processing with a small set of folks at Clemson University. So we use Slurm as a batch system and auto-expand the facilities there, running more than 1.1 million core on Amazon instances at Northern Virginia. So it was all unused instance. It was spot instances. And it was just using one region. Amazon currently has currently has 22 regions all across the world. So it effectively, for most of the scientific workflow, you can say that millions. You can model millions of cores with the infrastructure we currently have. So let me step back a little bit on the FPGAs. So LHC is now evolving to what we call phase 2. And so one of the ways the phase 2 is that their interaction, they're still colliding at 25 nanosecond, but the luminosity is going to increase. That means number of bunches in the particle is going to increase. And if you increase the number of bunches, you have to process a lot more. So at the level 1 trigger itself level, we see that each collision will produce roughly over 10 to the 3 particles. We'll have detectors of 10 to the 8 sensors, and at extreme data rate, it's roughly about 100 terabytes per second. So what you're trying to do is here, at the level 1 trigger level, we're inserting FPGAs, but trained it somewhere else, such that you can do machine learning inference directly here. And this way you reduce it. So I'll show you a couple of examples. So your trigger rate is, for example, 40 hertz. All you want to do is reconstruct events at 4 microsecond level. So that's what you'll try to do. So we added FPGA into the system so that folks can start working on it. And this is one of the diagrams, so in which the CPU does all the serial work, including recompiling the firmware, which gets loaded on using Amazon F1, so that you can quickly do the processing directly here. So in the past, physics was all about detecting particle and doing analysis based on patterns. And if you know a pattern, you call it a particle, right? Now the physics is going into, can I do physics using images, given convolutional neural net is so much matured? So what is shown here is a particle collision. When it collides, it creates a different kind of pattern. So once you have a pattern, based on a pattern, you can say this is a U particle or D particle or a Higgs boson. Now we're trying to work with this such that you can classify directly based on the images directly here. And here is the neural net definition, is the confusion matrix between predicted level, the true level. True level means you detected using some other means. Predicted level means that once you're predicting, as you can see, you can roughly process 600 images per second. So this is currently being developed and has been tried using Amazon F1 instances, basically dividing into a machine learning framework with HLS for ML conversion rate, which directly get inference using a given FPGA. There is also a workshop recently given at CERN of how to model this using Xilinx FPGA on AWS cloud. Also, people start using FPGAs in other cases. Imagine you want to do genomic sequencing. So if you want to do genomic sequencing for on a traditional CPUs, it can take weeks to months running thousands of CPUs. So these folks at Children's Hospital of Philadelphia, as well as EDCO-Genomics, they used Amazon F1 instance, which is FPGA, and got 1,000 pediatric genome sequence in 2.5 hours. So imagine how much it would have costed if you run it for months and years on standard CPUs instead doing on FPGAs. They got Guinness Book of World Record for the fastest analysis in the world. Quantum computation. Many folks ask this question, so I'll try to address a little bit. In a classical computation, you have a disk, you put a value in it, and you take it out, you get that value, right? Whatever comes in, the same thing goes out. In quantum case, when you put a given object, and if you're taking out from a different door, it changes phase space. So you may not get the same value. For example, if you put a red box, you may get a blue based on a given probability and the box you're taking out. Why do then? It's so complicated. Whenever it interacts with the world, it changes the phase. So what is so special about it? So one of the major advancement of quantum computation is what they call quantum entanglement. If you have two qubits, they're actually connected by a given interaction. You pull them apart to a larger distance, any deviation happening in one can change the other. And that's the biggest thing which we have shown in this world. Einstein called action at a distance, or Spookian's action at a distance. So imagine you want to build the best network in the world, the next generation network. I think quantum entanglement will be one of the way. And this was recently tested, that quantum teleportation was reported by European agencies, where they send one them to the space, other at the Earth, so that you can pass informations. Quantum also has a very interesting relationship with machine learning and deep learning. So most of the machine learning in a classical world, we start with a set of input layer. We try to model the correlation in the hidden layer and do an inference. In a quantum, things are already correlated in these circuits, so it's much faster to do that, especially the machine learning aspects there. So it's like reading a book. In a classical world, when you start reading a book, you know the story at the end of the book. So you start page 1, page 2, and all. But in a quantum world, if you do that, maybe page 10 changes the story. So the only way truth in the quantum world is read all the pages at once, so you understand the correlations. So quantum is extremely vital. People started using Amazon AWS for simulating many-body quantum dynamics. But it has huge applications in machine learning, in artificial intelligence. All the chemistry stuff is actually quantum. We model it in classical way. The same thing, biochemistry, finance, many other healthcare areas are extremely vital. So I'll quickly change subject and talk about how do we collaborate with other researchers. So to talk a little bit about research collaboration, we initially started one of the collaboration was with AMP Lab. So AMP stands for Algorithm, Machine, and People. And we were one of the founding members for that. And Apache Spark, ML Base, all of Spark, they all came from that collaboration. I'm so sorry. What happened? So this all came from that particular collaboration. Recently, we extended our collaboration to what we call RICE Lab, Real-Time Intelligent Execution System, such that whatever happens at a given observational level, it uses reinforcement learning, so it's a reward-based system. One learns the entire aspects, but provides the feedback into the system. So this way, it's an auto-feedback system using reinforcement learning. We also, as Dan talked about Frontera, so I'll not talk about it. So we have a plan to collaborate with Frontera as an auto expansion capabilities. Hopefully there's not a single person sitting and expanding it. We also are doing same thing with Expanse. Expanse is another supercomputing center, supercomputer which was funded this year at STSC. So here we are trying to do is to use auto expansion using scheduler-based mechanism. We started also collaborating with Open Science, Open Storage Networks. So these are the DTNs across universities which can interact with each other, but also interact with the lakes or cloud. So in this particular aspect, it is interacting with AWS, but also we are trying to put certain software at the DTN itself so that you can cache at a local node. Another thing we are also looking at is what are the other edge-based studies we can do. So NSF just funded STSC with this grant to use edge-based computing, but integrating edge networks as well. So they're going to use AWS Outpost. If you know or not, Outpost is like a cloud environment, but at on-prem with the same kind of virtualization and others. So one get access to compute, storage, networking, and all. It's as simple as we send to you the whole rack based on the specification you gave. You configure, connect, launch, and build. We also started collaborating with Globus. Globus has Globus Connect and other protocols such that researchers tend to use that as an authentication layer, as well as layer for storing or data transfer. So recently we started collaborating. They built an interface with Amazon S3, which is our storage system. We started work, Dan talked a little bit about multi-messenger astrophysics. So multi-messenger astrophysics is one of the top 10 ideas which funding agencies and researchers are pushing. So what does it mean? In astro world, as you can imagine, people get different kind of radiations, right? Somebody gets the infrared, somebody gets the ultraviolet. So what it means is basically you're getting different messages from different messengers. And two of the messengers are extremely vital. One is the gravitational waves as well as the neutrinos. And if you see this particular region, this is completely transparent to most of the electromagnetic and other areas. So that means any new observation, most likely chances are one can get via messengers like neutrinos as well as gravitational waves. And it's not that complicated. Neutrinos go straight, so you can point back to the sources. Gravitational wave tend to point back to sources as long as you model it. So this is one of the award called EGA, where for such study, you need exascale computing. So with NSF as well as UCSD, we are studying how do we model such simulation using AWS, using bursting to GPUs. But there are other providers that are also involved. So the technique is very simple. The IceCube sends its jobs to scheduler. Scheduler, negotiator looks at it and bursts to AWS and shrinks it back when the job is done. We recently demonstrated running at 90,000 runs. A few days ago, these results came in. We plan to show the scaling for exascale by the supercomputing conference next week. We're also working on data observatories with international organizations. So this is one of them, where one of the goal was to understand what the matter is made out of. As you may know, there are 24% in the world is dark matter, 71% is dark energy, and what we all know is roughly about 4% are all. So there is 90%, 95% of things we don't know. So this is one of the attempts to bring all the data together to understand dark matter and dark energy. This we are doing in collaboration with the Chilean initiatives. And one of the goals is to bring ALMA, various other observatory in Chile together such that you can understand multi-messenger astrophysics, but at the same time do the analytics using the same data environment. We also recently started collaborating with NSF on many of the programs. One of the programs was on big data. This is supported by multiple directorates. Currently, for last Maybe it got turned off. Sorry. So how many people you know spoofing? OK. So if those who don't know, imagine you want to buy a stock. Stock cost is $10. But you have no interest to buy it. You just put a price of, I don't know, $11. So you artificially manipulate the market. So it's a crime. So one of the ways to study that, and roughly about 70 billion transactions happens every day. So how do you detect that? So we started working in collaboration where we use something called generative adversarial network, GNs, to kind of have a real image and a classified image such that the discriminator can detect it's real or fake. And we recently are trying to apply that to detect spoofing at a real time. So this is the example where you're trying to buy or sell, but you have no intention to do that. With eCache, several projects we are working on, including bioinformatics as well. With NIH also, we started with Data Commons project with several of the members here. Then we started working with Kids First. So Kids First, if you know or not, this is one of the goals of Kids First program is to develop large-scale data resource to help researchers uncover new insight into biology of childhood cancer and structural birth defects. We also collaborate with 1,000 Genome Project. This is in collaboration. Many countries are involved, including United States, Britain, and China. Also, we have several collaboration on cancer genome resource as well as a microbiome project. How many people know microbiome? OK, that's your gut. So there is a saying that there are roughly about 10 times as many as bacteria, virus, and fungi that live within us than our number of cells. And they are responsible for humans, for digestion, but also many can cause disease-causing bacteria. We also work with Baylor for sequencing many of this, supporting more than 300 researchers across the world. I recently started collaborating with Harvard on precision medicine. But as you know, in order to do precision medicine, you need auto de-identification, right? So these are the 18 parameters for PHI. We use topic modeling to auto de-identify those parameters. So this is in one example. Imagine this is the chest X-ray of the person. His name is such and such. Age is a given value. If you use topic modeling and Amazon SageMaker, you auto de-identify it. With NIH, we started collaborating on what we call strides. So one of the major goals of the strides is to bring major data sets at a single place and develop analytic pipelines for researchers to use it. It has currently 4 phases. One is the discovery phase, accounting phase, as data migration, as well as research phase. These are the example of some of the data sets which are planned to be there. The goal is basically the metadata should be available to anyone who is trying to work on that. At the same time, build analytic pipelines such that people can use a centralized mechanism to analyze it, but also they can also contribute into this infrastructure. So there is a cookbook how to get started with NIH strides using cloud. And one of the major goals is to live in a world of connected data sets where all the data sets can be in a single place so that people can study correlation in science as well as do discoveries. One of the patterns we see most of the time is folks are interested in what we call research gateways or science gateways. This is all the lessons from Dan's slides, that this is all about lowering the barrier to cloud. So here is one of the things, it's called Red Cloud. Red Cloud, it's an open source, anyone can use it. All it does is provides a mechanism to have a secure cloud computing, but with a lower barrier to authentication as well as healthcare-related access. Here is another example. Welcome to AWS at Emory. So again, it's a portal-based mechanism with simplified access layer. We started working on Sky Server. So this is it's a container-based mechanism, which is currently planned to be transitioning completely to AWS. One of the goals is it's fully containerized mechanism. And one of the goals is to have a federated identity plus run everything, all the tools, as you can see here, as well as data sets in an environment such that you can share it. We are also working to provide ourselves those simplified access using federated identities. So currently, we are interfaced with OpenID, SAML, and various other identity mechanisms. We are also working with templates such that imagine you want a secure environment, you get those secure environment. You want debugging environment, you get that. So basically, the admin account controls all the templates. And when a researcher requests that I want a standard environment or secure environment, he gets that particular environment. So this way, the admin can control the cost. Admin can also do automatic vetting for accounts and various controls. So if you want to get started, there are many ways to get started. So a few examples I can give. Apply for cloud credit for research program. So this is you just have to send one paragraph to this link, and we will and give what you want to do, and we'll give a credit, and we'll also try to help you in your projects. There are also many other ways to use AWS. For example, there are AWS Machine Learning Awards if you're interested to apply there, as well as Amazon Research Awards. But for teaching also, we have AWS Educate and other mechanisms to communicate. With that, thank you. Are there any questions?
Hi, Sanjay. Yep, we have a couple of questions in the queue. Let me go ahead and read those aloud. So how can we get started with scientific computing in AWS?
That's a very good question. There are many ways to get started. So if you're at a researcher's level, contact your AWS account manager. Based on the project, you can get started. If you are at a let's say group or a collaboration level, one of the ways to get started is one of the ways to get started will be to write a project and apply for the grants, and we will help you in the process. But if you're at a large-scale organization like TAC and all, of course, we'll work for more formal engagements.
Great. Second question. What does medium-term collaboration look like between AWS and Frontera?
Thank you for asking. Dan mentioned it. So in the shorter medium term, what will happen is, I think, we'll have a portal at TAC. So we will send all the users to that portal. Once you have a login, then between Frontera and AWS, we'll figure it out what is the best way to host it while we are working on automation.
Perfect. Are there any other questions that anybody would like to enter into the queue? For our virtual audience, go ahead and feel free to enter them into the chat, and I'll be happy to read them aloud. Any live audience questions? All right. Well, I think then
Thank you so much.
Good to go. Our series, you can feel free to look us up. We are on